So, the premise of this chapter, where we start at least, are what we call the double angle identities. So, what we mean by that is if I have sine of 2 times some angle, is there anything that I can do to simplify or rewrite this? Well, if we remember our angle sum identity from our last chapter, then maybe if I can rewrite this as a sum, then yes, I have a formula for that. And so if I think of sine of 2 times an angle and realize that that's the same as sine of just that angle added to itself, then I can use the angle sum formula for there to get our expression sine of a cosine of the second angle, but that's still just a plus sine of a times cosine of a. And really, I think we were used to writing cosine of a times sine of a, but multiplication, so the order doesn't matter, so I can write that another way is fine. So I'm just adding sine of a cosine of a to sine of a cosine of a, which again, I can just write as 2 times sine of a times cosine of a. So now we have this new identity that actually isn't that different from what we already looked at before. It just turns out that things simplify to be a lot cleaner. So technically, yeah, anytime that you saw 2 of an angle, you could have said, okay, well, I know that's just an angle that I know plus itself, so I can figure that out. So if I said sine of, if we pretend that we don't know 120, you say, okay, well, that's just 60 plus 60. And we could have done that already. But now, instead of trying to do like up here, if we have it simplified to this step, then that saves us maybe a little bit of work. Either way, that is our double angle. Why did it erase those parts? Either way, that is our double angle for sine. We also have a double angle for cosine. And the double angle for cosine may be the most interesting. So we remember cosine of 2a, we can just do just like we did sine before, and say that's cosine of a plus a, cosine of a plus a. So our formula for angle sum for cosine is cosine of a times cosine of a minus sine of a times sine of a. And we remember multiplying something by itself is just what we call squaring. So I can rewrite this as cosine squared of a minus sine squared of a. Now, you may notice that this looks really, really similar to what we call the Pythagorean identity. We're used to seeing sine squared plus cosine squared and just replacing that with 1. So maybe you see this and feel like, oh, is there supposed to be some way that I'm supposed to simplify this? And you actually can. So we remember that we have those 2 different versions, well, sorry, 3 different ways that we sometimes end up writing the Pythagorean theorem. So we have sine squared plus cosine squared is equal to 1, where if I subtract sine from both sides, I get cosine squared is 1 minus sine squared. So if I use this version of it and plug that in here, then I'm saying cosine of 2a is also equal to 1 minus sine squared minus sine squared. But to subtract sine twice, we can just combine those into 1 minus 2 times sine squared of a. So cosine of 2a is equal to cosine squared minus sine squared and is equal to 1 minus 2 times sine squared. But again, if we look at our Pythagorean identity, then this shows us also if we would have subtracted cosine from both sides, then I get sine squared is equal to 1 minus cosine squared. So then here I can replace this sine squared with 1 minus cosine squared to get that my double angle for cosine is also cosine squared of A minus 1 minus cosine squared of A. And once I put the negative to both parts, this is cosine squared of A minus 1 plus cosine squared of A. So if I have 2 cosine squareds, then I can just write that as 2 times cosine squared of A minus 1. So the point is that we now have 3 ways of writing cosine of 2A. We have 3 equivalent things for our statement of the double angle for cosine. And all, well, really 2 of them, are really important to us for what we're going to do later in this chapter. But right now, we still do have these 3 formulas that we get to keep around. So just let's erase some of this to make it more clear what we actually care about. We have our double angle is can I just move individual things? Oh, what in the world? Let's try this. Incredible. So we have cosine of 2A is equal to 1. Where did the negative sign go? 1 minus 2 sine squared and 2 times cosine squared minus 1. Very good. Now we can do the same kind of approach with tangent of 2A and see this as an instance of our angle sum and see that's tangent of A plus A. So this is equal to tangent of A plus tangent of A over 1 minus tangent of A times tangent of A. And adding tangent to itself is the same as 2 times tangent of A, where multiplying tangent by itself we can write as tangent squared of A. So these are our double angle formulas for sine, cosine, and tangent. Now, what these mean is that if I ask you to find tangent of maybe 60 degrees, then this should be 2 times tangent of 30 degrees over 1 minus tangent squared of 30 degrees. And if you plugged in the values that we do know and simplified versus just looking at the unit circle, it turns out that these are in fact equal once you do all that work. But I'm going to spare us doing that actual work. That's just an example of how we can't find it. So random things got erased again. So in that instance, sorry, I'm having to undo a lot to get back to wherever I erased some things. Okay, there we go. Great. So the point is, if I ask you to find sine of some angle, 2 times some angle, and I told you what maybe cosine was, well, then we can go to our formula and say that sine of 2 times an angle should be sine of 2A times cosine A. Well, if I told you cosine of A, then you have that already. But if I told you cosine of an angle, we have that triangle method to figure out what sine of the angle is as well. So if I told you, for instance, cosine of, let's say, beta was 3/5, Then I can draw this triangle where I call this angle down here beta, and cosine is the ratio adjacent over hypotenuse. So the adjacent side would be 3, and the hypotenuse is 5. And I want to know this missing side, so I can use the Pythagorean theorem to say 3 squared plus b squared is equal to 5 squared. So that's 9 plus b squared is equal to 25. So I subtract 9 from both sides to get b squared is 25 minus 9 is 16. So b squared is 16. We say b is the square root of 16, which in this case turns out to just be 4. So this missing side is 4. And since I want to know sine of this angle, then sine should be opposite over hypotenuse. So this would imply that sine, in this specific question, sine of beta would have to be 4 over 5. Very good. So those are the basics of the double angles and just a little bit of review there with solving for these kinds of questions. So again, the cosine one is very interesting because you can use any of these 3 formulas and they're equally as valid. So say, for instance, I told you, let's see if I can only erase. Okay. That was a lot. Let's see if I can. Interesting. All right. So if I wanted you to find the double angle for cosine, and we have a question like this: find cosine of 2 theta if sine of theta is equal to 2/3. Well, you look at our double angle for cosine, and maybe you see the first one, and you say, okay, well, if I'm looking right here, then I need to know cosine. But also, if we look at the second one, all the second one requires is for you to know sine. So do you know what sine of the angle is? Yeah, it's right here. So cosine of 2 theta should be 1 minus 2 times 2/3 squared. And this is your answer. Alternatively, if I would have just given you cosine, maybe you look at the first and you say, oh, I don't know how to do that. Then you look at the second and you say, well, that one requires sine. And then you look at the third and you say, oh, well, there's one just involving cosine. Then you don't have to do any extra work there. So you kind of do get to have some free will almost when what you're wanting to do with your double angle for cosine in a way that you almost don't have with the sine or tangent. But sometimes it means when we have to make a choice. Now, well, there's the burden of making a choice. So we have to think about which one of these 3 formulas turns out to be the best use in the given situation. And again, that's just a general question of what do I need to know and what do I know? And just doing the, I don't want to say calculus, but the thinking there to figure out which one makes the most sense to you. Okay, so very good. That is the basics of our double angles. And in the next bit, we're going to use the fancy cosine double angles that we have to come up with reduction and half angle formulas.